Case Western Reserve University's Great Thinkers series proudly presents the Origins Science Scholars Program. These lectures are presented by the Institute for the Science of Origins, a partnership of Case Western Reserve University and the Cleveland Museum of Natural History, with the generous support of Richard Morrison and the assistance of Case Western Reserve University's College of Arts and Sciences, MediaVision, and WVIZ PBS and 90.3 WCPN IdeaStream. Welcome to the Origins Science Scholars Program, a series of talks on current research topics in origin sciences. Hello, my name is Glenn Starkman, Director of the Institute for the Science of Origins, and I am pleased to serve as your host for this series. The talk you're about to watch is entitled The Future of the Universe. In this talk, Evalyn Gates, Executive Director and CEO of the Cleveland Museum of Natural History, and a fellow of the Institute for the Science of Origins, will tell you about how the objects in our universe and the universe as a whole will evolve into the distant future. Please enjoy the talk.
Thank you to all of you who are here tonight because you're obviously very brave souls. We're going to have some fun tonight, but we are jumping out about as far as you can go from home and from the current point in time, which means we need to be a little bit brave and a little bit adventurous. So I want to start tonight with where you ended or could have ended the last time, here on our own planet. And I'm going to read a description of the universe on January 1st, 7 billion AD, that was written by Fred Adams and Greg Laughlin in their book, The 5 Ages of the Universe, which I can recommend with the caveat that they didn't know about dark energy when they wrote it, so you have to make some adjustments. So picture, if you will, a roiling vision of the sun getting larger and larger on the screen in front of you. The new year rings in little cause for celebration. Nobody is present, even to mark its passing. Earth's surface is a torrid, unrecognizable wasteland. The sun has swelled to enormous size, so large that its seething red disk nearly fills the daytime sky. The planet Mercury and then Venus have already been obliterated. And now the tenuous outer reaches of the solar atmosphere are threatening to overtake the receding orbit of Earth. Earth's life-producing oceans have long since evaporated, first into a crushing, sterilizing blanket of water vapor, and then into space entirely. Only a barren rocky surface is left behind. One can still trace the faint remains of ancient shorelines, ocean basins, and the low-eroded remnants of the continents. By noon, the temperature reaches nearly 3,000 degrees Fahrenheit, and the rocky surface begins to melt. A patch of the surface which once cradled the forested moraines of southeastern Michigan has seen a great deal of change over the intervening billions of years. What was once the North American continent has long since been torn apart by the geologic rift which opened from Ontario to Louisiana and separated the old stable continental platform to produce a new expanse of seafloor. Now the face of an ancient cliff is weakened by the sun's intense heat. A slab of rock cleaves off, causing a landslide and exposing a perfectly preserved fossil of an oak leaf. This trace of a distant verdant world slowly melts away in the unyielding heat. Soon the entire Earth will be glowing a sullen, molten red. I just want to make sure you feel comfortable leaving Earth behind, because it's not going to be any place we want to be in a few billion years. But having said that, I also want to give you the caveat that where we may be and what we may be 2 billion, 3 billion, 5 billion years in the future when this happens is likely to be very different than we are today. Evolution does not stop. And remembering that modern humans have only been on this planet for a few 100,000 years, who knows what or where our descendants, if they're smart enough to find a new home before this happens to the Earth, what they will look like. But the overview, the really big picture we want to look at tonight is what is the ultimate fate of the universe, the entire universe. And answering this question has been incredibly complicated by a group of physicists, 3 of whom, the leaders of 2 different groups, won the Nobel Prize in Physics this year. And what they found has told us that we don't know the answer to this question yet, and we thought we would by this time. But we don't know it in a way that we can predict very far into the future. We've got a pretty good idea, and then we have to step off. So when we're looking at the universe as a whole, when you're looking at this image, this is a Hubble Deep Space image, you're seeing a snapshot in time. You're seeing the universe as it is now, and we are in the middle of an era that's filled with stars and galaxies. It's the beginning of this era in time, and this picture of the universe will not be here in the future. So I want to warn you that most of what I'm going to tell you is based on a solid understanding of the universe and supported by a wealth of data from the subatomic realm out to the vast expanses of the cosmos and the observations that we've made. However, at times, and as we peer further into the future and deeper into the realm of quantum gravity, which we don't yet understand, this is a warning that used to be on old maps for explorers venturing across the oceans, and I want to put it here in a couple of places. Here there be dragons. And at the Cleveland Museum of Natural History, a dragon looks like a dinosaur. I also want to give you a little hint with numbers. The numbers we are talking about, the years we're going to go into the future, I can no longer use words like millions and billions and trillions because we are going much, 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 much further than that. So I just want to cue you in that when I talk about numbers and years in the future, a million, a 1 followed by 6 zeros, is an exponential notation 10 to the 6. I can go up to trillion in terms of words, which is 10 to the 12, but we are going beyond 10 to the 100. So that's about as big as we can go. Now, there are a couple ways to look at the universe and its past and its future, and I want to first give you an astrophysicist view, as opposed to a cosmologist view, and I fall more into the cosmology camp, which is probably why I had so much fun playing around with the astrophysics view. An astrophysicist is looking at the universe and saying, what's in it? What kinds of things, stars, particles, exist? And in doing so, a couple of researchers, Fred Adams and Greg Laughlin, about 15 years ago, broke it down into 5 distinct ages of the universe. And they started with the Primordial era and the Stelliferous era, which we're going to go into detail into all of these in a bit. And we are just at the beginning of that second era. So most of the universe's future has yet to unfold in front of us. And in looking at each one of these things, the one thing that you'll note is that the time scales get longer and longer. And the event rates at which things happen get longer and longer in time. So I find this a very interesting way to think about it. In the very early universe, a whole lot happened in the first 3 minutes. 3 minutes can go by in the universe today, and while that may be important to you or me, it really doesn't matter on the cosmic scales. But in the very early universe, it was absolutely crucial. But what's crucial to us today, things that happen in a few billion years, as we go further and further into the future, that's going to be nothing. That's going to be like a fraction of a second to us today. So the universe, even thinking about time, is going to change as we go forward. So the first thing we have to do is start and look at the past, and look at the ages that we have mapped out and that we do know very well. This is sort of my view of a very brief history of time, starting at the beginning of that cone, which is drawn to sort of indicate an expanding space-time that started 13.7 billion years ago and ends in the universe that we see around us today when we look at those beautiful Hubble images. And on this map, where there are a lot of sort of key markers noted for things that are happening that are interesting to cosmologists, there's basically just 2 eras for an astrophysicist. The first one is the Primordial era, which lasted before the first stars were formed. So Stelliferous means stars, and this is the era of stars began a few 100 million years after the Big Bang. So if we go forward, I want to talk to you a little bit about each one of these eras and what you might happen to find in them. So during the Primordial era, which starts from as far back as our physics can take us, so we don't actually know yet what came before the Big Bang, or exactly how that first instant of time where t goes to 0, but we can get almost arbitrarily close to that. And at that point in time, the universe was homogeneous. It was the same just about everywhere. And it was essentially a hot soup of all the basic particles that could possibly exist. So I'm showing you there my can of Campbell's soup. I do have actually 2 cans of that, and if somebody's really hungry, let me know. They've been sitting on my shelf for 20 years, not long by cosmological standards, but I'm not opening it. And actually the ingredients read on the side, photons, neutrinos, electrons. And they're right in one sense, but I'm still not eating it. So what there are is, it's a very violent place. You have particles, and they're constantly colliding with one another, scattering off one another. You'll have an electron and its antimatter particle collide together and disappear in a poof of energy that may produce 2 photons or may produce 2 other particles. You have dark matter, anti-dark matter, everything's colliding into everything else, bouncing around. The temperatures are unimaginably high. But the universe is expanding. Space itself is increasing. And as the universe expands, this hot soup, essentially a hot gas, expands and cools, just like any other hot gas cools. And as things cool down, other things can begin to condense out of it. So in this expanding universe, you have first condensing out of this quarks, which come together, 3 quarks will come together and form a proton. They're doing this in the very, very early universe, but as soon as they do that, something smacks into them and knocks them apart again. But as the universe cools, there's no other particles around with enough energy to break them apart, and you begin to form the basic nuclear particles like protons and neutrons. It continues to cool. It continues to condense. You form hydrogen atoms. You begin to form clouds of gas and dust, and these clouds of gas and dust can begin to collapse on their own weight. So a few million years after the Big Bang, these large clouds, molecular clouds of gas, collapse under their own gravity to form the very first stars. And this signals the beginning of a new era, the Stelliferous era, the era of stars and of life as we know it. So this is an image of Hubble Space Telescope of the Carina Nebula, and this just shows you one place where stars are still being born today. These are pillars of gas and dust, and they're being sculpted by the incredible radiation and winds of nearby stars that are forming and living brief lives before exploding again. And what's going on during this entire era of stars is stars are being created, they're forming. Sometimes people talk about them being born, they live out their lives, and they die in very spectacular ways. So the basics of what's in the universe at this time are stars, which are mainly hydrogen gas, and they burn this hydrogen as a fuel for as long as they can to counteract gravity, which wants to collapse them even further. The very first stars, which we're just beginning to get hints of seeing in the very earliest protogalaxies, were probably very extremely massive, 100 times as massive as the sun, for example. And the more massive a star is, the shorter its lifetime. Massive stars burn through their fuel at incredible rates. So for a star like these first stars, they may have lived only a million years or a few million years. That's really, really short in cosmological times. And I wanted to show you this. This is another Hubble Space Telescope image. And this is of a galaxy that's acting as a gravitational lens and lensing into view one of the most distant galaxies that we've ever seen. So in those circles, there are little red dots, and those little red dots are of galaxies, and the stars in those galaxies formed about 200 million years after the Big Bang. So we're actually now getting to the point, and once the James Webb Telescope comes online, we are going to be able to see this era of the very first stars forming. We're going to be able to probe directly back and get images of the very beginning of the Stelliferous era. Now, as I said, lifetimes for stars depend on their size, and they range from a few million years for the most massive to trillions of years for the least massive stars. So there were stars that were formed in the early universe that are still burning hydrogen very, very slowly and carefully today, and they are going to continue long after the Earth and the Sun are gone. And new generations, there's a kind of cosmic recycling that goes on. As a star ends its life, it returns sometimes most of, or half of, or at least some of its materials to the interstellar material, the gas and dust between the stars, which then eventually will form new stars. So we're going through this cycle of constantly forming stars. Stars are born. Stars like the sun will go out in a beautiful planetary nebula. They blow off a lot of their materials. They become red giants, blow off gas and dust, and eventually then the inner core collapses to form something called a white dwarf star. Much more massive stars, more than about 10 times the mass of the sun, go out with a huge stellar explosion called a supernovae, and those are going to be important to talk about in just a minute. But the stars are being created, they cycle through their fuel, they either explode as supernovae, they go red giant, become white dwarfs, and this continues because galaxies have a lot of gas in them. They've got huge gas reservoirs. So we're making new stars, stars are burning, they're going out, but eventually the galaxies are going to run out of these gas reservoirs. And the formation of new stars will essentially come to an end. squinting, I can't see how much time I have left, but we'll keep going. At the end of this era, as the last low-mass stars run out of fuel, trillions of years from now, there will be no more shining stars, almost. And we're going to enter something called the Degenerate era, which has got nothing to do with partying or having a good time, it's actually going to be a less friendly place for people. But what you're going to have in the universe at this time, from trillions of years to 10 to the 39 years after that, is an age of stellar remnants. Most of the universe is going to be in the form of white dwarf stars, stars like the sun or slightly less massive stars that form these cooling embers. These are just balls of the core parts of stars, a lot of carbon, oxygen, and all they do is slowly cool over trillions more years. Brown dwarfs, which are star wannabes. Sometimes when a cloud of gas collapses, it's not massive enough to have enough gravity to really heat the core and form a star that's burning fuel. Neutron stars are stars more massive than the sun. At the end of a supernova explosion, you're left with either a neutron star or a black hole. The time scales continue to expand, but the action continues. So I'll finish with this and then we'll go on. The galaxies are colliding and merging, and then galaxies themselves begin to evaporate.
How do you reconcile your conclusions on this analysis with the vast amount of dark energy and dark matter that permeates the universe?
There is dark matter in the universe, and we've got some good evidence that there's dark energy, and that's going to be really important when we look at the cosmological picture. But we know that whatever the stars are made out of, it's essentially normal matter, made of hydrogen, neutrons, protons. Dark matter has to be something very different than those, and dark energy is not matter of any kind. So in these stellar explosions, what you're doing is producing more and sometimes different forms of dark matter, or of normal matter, which is really important for all of us because the iron in your blood, a lot of the heavier elements, they've all been processed through these generations of stars. You've probably heard the expression that we're stardust, and that's because of the Stelliferous era. The things that formed the Earth, the metals, the heavy elements, all came from earlier generations of stars, but it's not related to dark matter and dark energy.
You mentioned that the stars, after the hydrogen is burned up, they're just a dense mass. What is that mass?
They've run out of hydrogen, and they'll burn through most of their helium, and what's left in the case of stars like the sun is carbon and oxygen, and over time they start out tens of thousands of degrees, very hot, just balls of normal matter, and they can't collapse any further because of something called electron degeneracy. So the degenerate era refers to the fact that quantum mechanics says that electrons don't like to be squeezed too tightly together. They resist very strongly. And so these things collapse under gravity until you've got too many electrons crammed in together and they can't collapse anymore.
Thank you for joining us. You have been watching Dr. Evalyn Gates of the Cleveland Museum of Natural History discussing the future of the universe. For more information on the Origins Science Scholars Program, please visit the Institute's website at www.case.edu/origins. In the first part of her talk, Dr. Gates guided us from the distant past into the far future, when all that will exist is massive black holes at the center of galaxies and the far-flung ashes of burned-out or dim stars. In the second part, Dr. Gates will tell us what happens as those black holes begin to radiate away their energy, leaving us with a universe that is dark, cold, and nearly empty. Now we return to the lecture.
I want to tell you what's happening to galaxies. So galaxies, hundreds of billions of stars, the stars have gone out. You've got all these remnants floating around, white dwarfs, brown dwarfs, and some black holes in here. But what happens is every now and then they come close to one another and have a collision. And this takes an incredibly long time to happen because most stars, right now we look around, we aren't seeing too many stars collide, but the time scales are much longer. So even though it's low probability, it does happen. And when it happens, usually one star gets a little kick and may zoom completely out of the galaxy, and one may sort of lose energy and fall to the center. So most of the stars over time will evaporate. They're going to get kicked out of the galaxy, and the remaining will fall to the center, where lurking there like Cookie Monster is a big supermassive black hole that's just waiting to gobble up anything that begins to fall down into it. So occasionally, when I said there are no more stars, occasionally, like every 100 billion years or so, 2 brown dwarfs, these star wannabes, which are mostly hydrogen still because they haven't burned any hydrogen, they never lit up, will collide and produce a new star. And this new star will then burn for a few trillion years. But again, that's a drop in the bucket in the overall age of this era. What's interesting, though, is this collision may even produce planets or solar systems. They're going to be orbiting around these red dwarf stars, which are low mass, they're stable and warm enough. You could have an entire new generation of life or some form of life starting in this era. Or, if we're really clever, maybe we found some way to latch onto one of these. So what you're seeing in a galaxy, if you were to look out, it's going to be mainly very, very faint. Instead of those beautiful images we see in Hubble of hundreds of billions of stars glowing, very, very faint infrared glow from most of the remnants, with 100 or so, not 100 billion, but 100 or so stars actually burning, and an occasional supernovae from the collision of 2 white dwarfs. And this big hunkin' black hole in the very center. Now, the end of this era is going to come about probably through proton decay. Protons, these basic nuclear particles, we have never seen one decay yet, but a lot of our theories about how the subatomic world works predicts that they are going to decay eventually. And when that happens, these white dwarfs that someone just asked about, they're made of things like carbon, which are protons and neutrons. When those particles decay, these remnants will just evaporate away. There will be nothing left. We know that this proton decay, there's a little hint down at the bottom. That's one of my little tags. Here there be dragons. We don't know exactly when protons will decay. There's no guarantee that they do, although it seems a reasonable assumption to make that at some point they will, because there are several different ways that this could happen. But basically, once they've decayed into essentially light particles and positrons, you have no more remnants in the universe. You will only have a diffuse sea, a very cold, dark universe filled with light and electrons, positrons, neutrinos, and black holes. And when the last of these stellar remnants evaporates away through proton decay, the black hole era begins. The universe is now 10 to the 40 years old, or more. And you've got a universe that's filled galaxies with maybe 1 million black holes orbiting around this supermassive black hole at the very center of the galaxy. But black holes also don't live forever. They're not really black. And this is one of the great works by Stephen Hawking, who demonstrated that due to quantum mechanics, black holes actually emit radiation, they evaporate, and the more massive they are, the more slowly this happens. So as a black hole evaporates, it gets slower and slower, and the speed at which it radiates gets faster and faster, and they're completely gone at the very end. So this evaporation is happening due to quantum mechanics, and that can be part of the question maybe after dinner. But by 10 to the 100 years, even the most massive black holes at the center of galaxies will be gone, and the universe enters its final age, the dark era. We are now at 10 to the 100 years or more. The cosmos is dark, it's cold, and it's almost nearly empty. You've got photons and neutrinos with an occasional electron and positron spread extremely thinly through space. There may also be some dark matter. We don't yet know exactly if that's also going to decay away when the protons, so we can't say for sure. We need to know more about it. But this density of particles, whatever out there, is really low, and to give you an idea, there will be less than 1 particle in an entire volume of space that is 10 to the 104 times larger than the entire universe we can see around us today. That's a pretty boring place. Nothing happens. There's nothing to collide. There's nothing to burn. There's nothing more to evaporate to, or does it? So, we need to come back to the present era, because the question about dark energy is spot on. And this has thrown the monkey wrench into all of our understanding of the universe. That endpoint I described is still probably the most likely scenario, but we don't know. And here's why we don't know. So in 1929, Edwin Hubble went out and measured distant galaxies and the rate at which they were moving. And he found they're all moving away from us. Those that are further are moving away faster. And the understanding is that we live in an expanding universe. Space itself is increasing. It's kind of hard to get your mind around, but But mathematically, it works beautifully, and observationally, we've had it confirmed over and over again to increasing precision. Now, what we expected up until the late 1990s was that the universe is expanding. It has stuff in it. We can see galaxies and stars, and all that stuff is attracted to all the other stuff. So it's putting a friction on this expansion. The universe is expanding. Gravity wants to pull all these things back together. The expansion of the universe should be slowing down. But new measurements showed exactly the opposite. The universe is not slowing down, it's speeding up. And this is the observation in 1998 that was just awarded the 2011 Nobel Prize in Physics to these three individuals who were the head of two different teams. And what they were doing is going out and looking at very distant exploding stars called supernovae and measuring how fast the universe is expanding in the past. The further away you look in the universe, the further back in time you're looking. So they needed to look at ever more distant objects in the universe and measure how fast they're moving away from us in order to understand how the expansion rate of the universe has changed. And they went out expecting to see that the universe was slowing down. Basically, it's really simple. The image down there is a galaxy, and in the outskirts of that galaxy, you see a bright object. That's a star that's gone supernova. For a month or two, it will shine more brightly at times than the entire galaxy full of hundreds of billions of stars. These are incredibly powerful explosions. That means they're really bright, so you can see them very, very far away. And we understand enough about them to know how bright they should be. And that allows us to use them as standard or standardizable candles, so we can determine how far away they are because we know how bright they should be, and we observe how bright they look. And the fact that they're dimmer means that they're give us an idea of how far away they are. And so that's what these two groups of astronomers did. They went out and measured the expansion of the universe, and what they found was that about 5 billion years ago, the universe was slowing down until that point, because they've measured even further back in time. You see the universe expanding, it slows down. About 5 billion years ago, it kicks it up into high gear and begins accelerating. And this was named, even in 1998, the Science magazine's Breakthrough of the Year, because this is worth a Nobel Prize, and it is revolutionary. It's telling us there's something in the universe that we've called dark energy, for lack of a better name, that's dominating the universe. So it's not just a little bit of it out there. Most of the universe is in this stuff, and it's causing the universe to expand at an ever-accelerated rate. And why that is so interesting is because we don't know what it is. So it could be several things. A lot of theories have been proposed. It could be, for example, an energy of empty space itself, similar to Einstein's cosmological constant. We know from quantum mechanics that empty space is not empty, but you have particles that are bubbling in and out of existence all the time. And these virtual particles, there's a certain vacuum energy and energy of empty space. The problem is when we calculate it using quantum mechanics and what we know about the subatomic world, we're a little bit off in comparison to what these guys observed. In fact, we're off by 120 orders of magnitude. So even for a cosmologist, that's a little bit too far. We can put in other theories, supersymmetry, and bring it down to being only 60 orders of magnitude off. It's still too big. So while this is a great concept, we don't have a good physics model to explain it. It could be a new energy field that fills the entire universe that goes under the name of quintessence. It could be that it's time to think about some new theory of gravity, maybe Einstein's theory, which works extremely well as far as we've tested it. Maybe it's time to modify it. It could be something even stranger, extra dimensions. There are many interesting models that people have come up yet. The bottom line, though, is we don't know what dark energy is. But we do know that whatever it is, it's new physics. We can't explain it by anything that we already know. And that means it's going to lead us to some incredibly new understanding of space and time at its most fundamental level. But even more importantly, because we don't know what dark energy is and we don't know what the nature of it is, it fills the universe. 72% of the universe, I'll come to that later, is in the form of dark energy. And this dark energy is controlling the expansion rate of the universe. And until we know what it is, we don't know how it's going to behave over the next 10 to the 100 years, and so we don't know what the ultimate fate is. It could expand forever, continuing to accelerate. It could actually still end in a big crunch, where the universe expands to a certain size, slows down, turns around, and recollapses on itself in a huge crunch where everything goes back into a very, very small, hot place, not good for us. There are other ideas. about how the universe might end. And so what I want to do now is just tell you a little bit about some of these ideas. So we used to think that in a universe that was filled with only matter and radiation, which is everything that we've detected so far, that if we knew the overall geometry of space, we would know what its ultimate fate was. And this is because, according to Einstein's theory, how much stuff is in the universe tells you what its overall curvature or shape is. Matter and energy warp space, and space in turn warp space tells matter and energy how to move around. But the important thing here is that matter and energy are warping space, including on the level of the entire universe. And the expansion of the universe depends on exactly what's in it. So if we can measure the geometry, we know how much total stuff is in there. And by looking at sort of how the fact that we're until recently in a matter-dominated universe, we would know how it would, the next 10 to the 100 years would proceed. And I'm going to give you a quick image because this is actually easier to understand, I think, than it sounds. So if you want to measure the geometry of the universe, to me it's mind-boggling that we've actually gone out there and done it. And by geometry, I mean if I were to stand in empty space somewhere and send out two rays of light that were parallel to one another, go back to your 8th grade geometry, do they remain parallel forever? Or, and if I were to create a triangle in those spaces, would the sum of the angles add up to 180 degrees or not? So the three big options you have for the geometry of the universe, and I'm showing you 2 dimensions here because I can't draw this in 3 dimensions, and our brains really have trouble picturing that this way, so there's limitations to this. But a universe that has a critical amount of density, it's got just the right amount of stuff in it, is what we call flat. And flat means that all of your middle school, junior high algebra and geometry work. If there's more stuff in the universe than this, it's a closed universe, and it's curved like a sphere, but in 3 dimensions. So this just gives you an image. And in such a surface, if you were to draw a triangle on that surface, you're going to find out that the angles add up to more than 180 degrees. And parallel lines will meet. If it has less than this critical density, you get this sort of saddle-shaped universe in the bottom, and angles there are less. So what we want to do is to go out in the universe, take a big expanse of essentially empty space, and take something whose length we know, because on these 3 examples, the length L is the same in all of them, and we know the distance to that thing, and then measure the angle that it subtends on the sky. And once you do that, you can tell what the overall geometry of space was. And it turns out that we have such a ruler. What you're looking at is the afterglow of the Big Bang. This is called the cosmic microwave background. I'm sure it's familiar to some of you, but if you haven't seen it, this is an all-sky projection. So what you're looking at, this is oval. It's just when you look at a globe and they take a globe and map it onto a flat space, sometimes it looks like a big oval. Well, now instead you're inside the globe. You're looking at all of the sky around you and mapping it onto this oval. And what you're seeing is microwave detections where the red and the blue are different to about 1 part in 100,000 degrees. Tiny, tiny differences in temperature. Some spots are a little hotter, some spots are a little colder. But we know what a typical spot size would be based on just understanding the physics of the early universe at this time. So you're looking at the universe as it was 380,000 years after the Big Bang. It's an infant picture of the universe. And if I take a computer and say, okay, now if I'm looking at that infant universe, I know what it's supposed to look like. A typical spot size would be about 1 degree. But if I look at these spot size, and these are computer generations of what it would look like if I looked through a universe that had that open geometry, flat, or closed geometry. And the simplest thing is if you look at the closed, again, the angles, the size of those objects looks bigger than it does in a flat universe. So we have this incredibly high resolution picture of the infant universe. We know how big these typical spot sizes are. And what we found is that the typical spot size is about 1 degree, which is exactly what you expect for a flat universe. So we have, in essence, measured the overall geometry of the universe and found that it's flat. So that tells us that the total amount of matter and energy in the universe is equal to this critical density.
Is the entire universe expanding at the same rate? Is it uniform? Is expansion 4 billion light years from here expanding at the same rate as here? Is there globs?
The answer is yes, on sort of the scale of 4 billion light years away. As far as we can tell, in this overall area that we lived, it's more or less the same. Although there are caveats, like our own galaxy, for example, is not expanding away. It's once something is sort of gravitationally bound, it opts out of this overall expansion. So we have seen no hints that maybe it's expanding differently in a different part of the universe that's beyond what we can observe, but that's still a possibility. So we don't have a way to nail that down yet.
You have described a situation in which the universe is continuing to accelerate, so that it's expanding much faster, or at the present time, than it did in the remote past, or in the remote distance as we can view it. So does this, is the assumption being made that the entire universe is actually expanding the way the portions close to us seem to be expanding?
Yes. Now, we don't have to make that necessarily for our part of the universe in terms of looking at the overall expansion. So this is going back to the idea, some people have explored very carefully whether we're living in, say, a bubble that happens to be underdense relative to the rest of the universe, and that might explain why we think there's dark energy. The challenges to those kinds of ideas are that we have to be living right at the very center of a bubble region, and it has to be almost exactly spherical around us. So that these are the kinds of ideas people are looking at. It hasn't emerged as a strong contender yet. But we only know as far as we can observe in the universe.
We hope you've been enjoying the Origins Science Scholars Program with Dr. Evalyn Gates. Dr. Gates is the author of Einstein's Telescope, an exploration of how gravitational lenses can be used to learn more about our universe. In the second part of our talk, we learned how black holes will eventually decay away, leaving an almost completely empty universe. In our final segment, Dr. Gates will discuss how the recent discovery of dark energy makes it difficult for us to predict the ultimate fate of the universe as a whole. Now, back to Dr. Gates.
Coming back to the overall geometry, we know that the universe is flat, and this is what it contains. 72% of this dark energy, 5% of the normal stuff that you and I and the sun and the earth and everything we've ever detected directly is made of, and 23% of dark matter, which, for the purposes of this discussion and this lecture, you can lump all the matter together. It's the dark energy that's really important. So as a cosmologist, I'm looking at 3 major epochs in the universe, not the 5 ages quite that they're looking at from an astrophysics point of view. And that means an epoch that was dominated by radiation, by light, an era that was dominated by matter. That's extremely important because we didn't have a matter-dominated era, we wouldn't be here. It's only in those eras that you can form structures like galaxies and stars and planets. And then the dark energy epoch, which seems to be where we are right now. And as the universe expands, remember that the volume of space is increasing. And so one of the questions people often have is, if we've got radiation and matter and dark energy, were they always here? How has this changed over time? So in the very early universe, in the first 50,000 years, most of the universe was in the form of radiation. But as space itself increases, the volume of space increases, the density of stuff inside usually goes down. So the density of light particles goes down very quickly, because as it expands, you're not only having the same number of particles, say, in a larger volume of space, which decreases density, but you're also redshifting those photons. You're stretching their wavelengths, which makes their energy go down, which makes their energy density go down. So even though light and radiation was the main component very early in the universe, it got diluted away. The universe is expanding. So you had matter, which wasn't very important in the very early universe. It's diluting away as well, but not as fast as radiation. So about 50,000 years after the Big Bang, radiation is diluting faster. It's gone to smaller and smaller percent of the universe, whereas matter is becoming more and more important. So between 50,000 years and maybe 8 or 9 billion years after the Big Bang, matter was the main component in the universe. And it was during this era that we formed the stars and the galaxies and the planets and the people that live on some of those planets. Dark energy behaves very differently. It doesn't dilute away. It's energy of empty space itself. As you increase the volume of space, you increase, the density stays the same, a constant. That's why it's called a cosmological constant. The density, the energy density of dark energy stays the same. So it just sits there and waits. It waits, and the other things that are the major components get diluted away, and at some point, about 5 billion years ago, it emerges as the main component of the universe. And the question is, what's going to happen to dark energy in the future? If it is truly the energy of empty space, which is, I'm going to call this the simplest explanation, it's got an asterisk because, as I mentioned earlier, we don't have a really good physics theory underlying it to explain why it has the value it does and not either 0 or some really huge number. So with that caveat, this is Einstein's cosmological constant. So as the universe expands and the volume of space increases, this energy density in this vacuum stays constant. And that's what's fueling the acceleration of the universe. So if that's what happens, the universe continues to expand at an ever faster rate. But there's some interesting things that happen from our view, from our perch here in the Milky Way. So all of the stuff I talked about earlier in terms of how an astrophysicist sees things are going on. We're going through the Stelliferous era, we're going through the era of remnants. But what's happening at the same time in this accelerating universe is everything outside of our own little supercluster of galaxies is moving away from us at increasing rates. So in about 100 billion years, and so this is before even all the stars have gone out, the universe becomes a very dark place for us. We will be sitting here in a new galaxy that, the Milky Way and Andromeda are scheduled to collide and merge starting in about 5 billion years from now. So we're going to be sitting not on Earth, but on some other planet, hopefully a moon, in this galaxy and looking out, and there won't be anything to look at. We'll be able to see the stars in our own galaxy, and that's it. And Glenn and I were laughing a little bit earlier. This may be the end of cosmology, 0 employment for cosmologists, because we lose things to look at and get information about. As the universe gets older and older, we see the stars, and it looks like that's all there is. And unless we've got some kind of library that's preserved the information we have today, an astronomer, cosmologist looking out at the universe 100 billion years from now is going to come to very different conclusions about the universe in which they live, which I think is just kind of interesting from a philosophical point of view. Are we really lucky to live in the particular era we do when we can sort of look into the past to project the future? Or, are there things that are hidden from our view that we can't see because of where we live in time? And Glenn is going to fill you in later on all the details of life in a universe like this, as you get further into the future, what kind of life you might be able to have. There are other fates that are not ruled out yet. So if you notice, there was a small dinosaur here because we just don't know if dark energy is a cosmological constant. There's a little bit bigger dinosaur, or here there be dragon dinosaur in this one, because a big crunch. We don't know what dark energy is. It could be an energy field that decays into products that are more matter particles, in which case the universe will have more than the critical density of matter possibly, or it could, the value for this could change over time in some theories until it's a negative value, in which case the acceleration halts and the expansion reverses itself until things get closer and closer and closer and closer, hotter and denser until we end in a big crunch, kind of the opposite of the Big Bang. The earliest that could start happening based on the expansion and what we see around us today is about 20 million years. So we still have plenty of time. But I'm not talking billions of years now. This could actually change the scenario in millions of years. There's a huge dinosaur dragon on this one. There's another idea that's been out there called the dark energy being something called phantom energy. There are lots and lots of issues about how you get a physics model that's consistent and doesn't have all sorts of nasty little things like infinities and tachyons in it. But if it's this thing called phantom energy, where it gets more negative over time and increases, it doesn't stay constant, the energy density in vacuum energy would increase in this scenario, but you would end in a big rip. The universe is expanding faster and faster and faster, and it expands so that even things that are now gravitationally bound can no longer stay bound. And it begins to rip apart clusters and galaxies, then solar systems, then the stars, the planets, and atoms themselves will be ripped apart. That's about 30 billion years if we're going in this direction. On the other hand, maybe there isn't an end, and this is referring to the multiverses that were mentioned earlier. Maybe internal inflation, our universe is just part of a larger and eternally accelerating multiverse, and different small universes are popping out like our own. Our own could still end in a big crunch, and this other larger multiverse continues. And we just don't know enough about the physics of this to know how this might impact us going forward, or how we might try to continue life or existence of some kind in this accelerating multiverse. So the summary is, in the short term, we understand pretty well what the future is. The Earth is going to get toasted. The Milky Way and the Andromeda galaxies are going to merge, and the age of stars is going to come to an end. I think the most likely long-term future is that the universe is very cold. The temperature just keeps dropping to an almost unimaginably small fraction of a degree. It's very dark. There's nothing lighting it up. And it's nearly empty, with one particle at most in that huge volume of space I described earlier, more than 10 to the 104 times the size of the volume of our own universe. It accelerates forever, and nothing happens. It's very boring, which is not a way to end a talk. So I'm going to end here with the biggest dragon of all and just give you something to think about in a little bit different size. This dragon is one that's based on things that we don't understand well enough yet to really make this solid. So here we're going way out on a limb. These are ideas that are fun to talk about, but I personally think until we have a quantum theory of gravity, we're on thin ice here. But the idea is that if you wait long enough, the universe will empty out and stay that way forever. This is a quote that is coming from Eternity to Here, another excellent book I can recommend by Sean Carroll, a colleague and friend of Glenn and mine. And what he says, if we wait long enough, our universe will empty out and stay that way forever. There will be random fluctuations that will lead to all sorts of unlikely events. So in a quantum mechanical world, things can happen. Particles can pop in and out of existence, and even more complicated things that can. So unlikely events, including the spontaneous generation of galaxies, planets, and Boltzmann brains. A Boltzmann brain is just a brain that suddenly appears, gets consciousness in an otherwise empty and lonely universe. The chance that any one such thing happens at any particular time is almost vanishingly small, but if you've got forever to wait, every allowed thing is going to happen sooner or later. And including the fact that because you've got eternity in front of you, the overwhelming majority of even redheaded physicists will pop out of the surrounding chaos and find themselves drifting alone through space. And that may be the most likely end, but I think I'd rather be a physicist right now in this age of cosmological wealth. Thank you.
This lecture is part of the Origins Science Scholars Program of the Institute for the Science of Origins, a partnership of Case Western Reserve University and the Cleveland Museum of Natural History. It has been brought to you with the generous support of Richard Morrison and the assistance of Case Western Reserve University's College of Arts and Sciences, Media Vision, and WVIZ PBS and 90.3 WCPN IdeaStream. For more information on the Origins Science Scholars Program, including a full video archive, please visit the Institute's website at www.case.edu/origins.